Hi, today we're going to look at how to perform a quantification using the S1CalProcess plugin into Microsoft Excel. First, a couple notes. This is a plugin into Microsoft Excel, meaning that most normal functional Excel uses are present, but we've added a few using macros. You'll want to make sure your Excel version is compatible with macros and compatible with these particular macros. If you have any questions, please don't hesitate to contact us at Brooker. We're going to navigate the quantification structure for these spreadsheets. The first page of interest is labeled PDZ files. Here, in this window, you can see the name of each reference spectra, the time it was analyzed for, the Compton window, and then photon counts for a number of different elements. In fact, we can scroll through here, and you can see there are many, many, many elements. If you scroll to the very end, you will start to get diagnostic information, such as your valid and raw count rates, your energy and current parameters, the filter position in the software, the resolution in EV per channel at full width height maximum for manganese K alpha, and finally whether or not you have a vacuum, also the channel count. If we want to add spectra, we do so here. In fact, I can go up here to S1CalProcess, insert PDZ, and select a PDZ file to add. We're not going to do this yet. First, we're going to go through the normal default calibrations, and then we'll proceed to add a new spectrum. The next spec sheet to look at is GLChem, which is over here. Now, GLChem stands for General Linear Chemistry, GLChem. Your specific file may be CuChem or CopperChem, AlChem or Aluminum Chem. It really depends on how the sheet is spread up. Different calibration spreadsheets are set up in different ways. One thing that I strongly recommend is to use an existing calibration spreadsheet as a template for your own calibrations. Here in GLChem, if I come over here to the left, I have each reference spectra and then the name of each element present here. These are the photons for each element for the K shell in particular, though some, like barium, we use the L shell. Over here in the middle, I see coefficients, and to the far right, I see my known concentrations. So, if I wanted to get a simple calibration curve for, let's say, iron, I would select iron here, come over here to my known concentrations, and select that column, and insert a scatter plot. And there you see our simple linear chemistry. You see photon counts on the y-axis, and then iron concentration and weight percent here on the y. Now, notice all the data spreading? This is because there's lots of matrix and interelemental effects occurring in these samples. Here we're doing our reference spectra are geological samples themselves, not international standards. So they're not purified or homogenized in the same way. We're using like to calculate like. So this kind of spread is normal. Once we start normalizing to Compton, incorporating interelemental corrections, the correlation will tighten considerably, though when we start using other elements, it will also become multidimensional and thus not quite easy to show in a simple format, such as right here. In any case, if I come up here to add-ins and S1CalProcess, I can add, remove chemistry files. Here's where I remove different reference spectra for different calibration files. I can also add, remove elements, which is self-explanatory. I can take away lines and add them. Here, I'm going to show you how to create a chem file for our vacuum collected data. So this is data collected at 15 keV with a vacuum, no filter for a mudrock set. You can see here these standards are labeled with the dot with the dash MAG. We also have this dash MAG indicates major, dot dash TR indicates trace, and dash helium indicates helium spectrum. Here I have each calibration file. GL1 refers to vacuum, GL2 refers to trace, and GL3 is our helium calibration. Here in this window, I point to where my calibration spectrum are housed. It's important to keep all of your calibration spectrum in the same folder to be able to create a quantification file. If you do not do this, then you will not get your quantification. It's that simple. All reference spectra used in a calibration must be in the same folder. Here, I'm normalizing to a given Compton energy range, 2.8 to 3.1 keV. I can select Compton versus time, region of interest, etc. Compton, for oxide data, is generally better. Now, what does this mean exactly? Well, let's come over here to Artax and let's load up our reference spectrum. These are all the reference spectrum taken with vacuum conditions. If I expand here, I can begin to add my elements. Here, just correcting, I can see magnesium. I can see aluminum, silicon, phosphorus, sulfur, potassium, calcium, titanium, which is over here. The list goes on. Importantly, right here, I have my rhodium L line. In the calibration, I'm normalizing to this range between 2.8 and 3 keV. Why this range? Well, because it's primarily driven by rhodium and thus reflects background reasonably well. So for example, to show you how this works, I will click there, spectrum, normalize. And if I look, I create a nice baseline for all these elements to quantify. So that is what is happening here, 2.8 to 3.1 keV. Keep in mind, where you normalize to is perhaps one of the most important steps in a quantification procedure for X-ray fluorescence. It's also one of the most frequently neglected, at least that I've seen in my experience. We're going to highlight this a little bit later when we look at the helium cal, but for now we're going to use the defaults. I then click OK, and here I get my calibration, validation, and customization. Here to the far left, I have each element that I'm quantifying for. Here, I have each slope correction, and here I have each background correction. Here, I can remove standards for a given element. Finally, I've got my model validation, which is right here. Here is each element or reference standard. Here is the given concentrations in these reference standards. Here is the calculated values based on these parameters over here. And then here is the difference between the two. For example, if I come to magnesium, I'm having two slope corrections, one to magnesium, one to silicon, and then I'm having a background of magnesium and silicon. If I want to change these, I can over here. So for example, the simplest quantification of magnesium, I can see my given, my calculated, and then the difference between the two. And then down here, I have an average difference of 0.5, or half a weight percent. Not too bad. When I add in my slope correction, that goes down to 0.4. Here, I'll do it again so you can see. Without magnesium slope correction, with magnesium slope correction. So there I have an improvement to 0.42. Here I can add a silicon background correction, and I see a slight improvement. And then I have my silicon slope correction, which gets me down to 0.35 weight percent variation for magnesium. Not too bad. I can look over here and look for large deviances. So for example, if I come down here to RTCW99, I see my variance for this particular standard is negative 0.73. So I can remove it here, and I can look to see if that improves. While it does slightly improve my quantification, note that this is 2.5 weight percent. I want to be able to capture that range of variation, so I leave it in for now. But you can customize and look for reference standards that may not be the best to produce a quantification. I then go through here And as I go through each element, I get the different corrections. And you see this little asterisk? This asterisk means that, that I've reviewed that element. If I try to save without checking all the elements, it will not produce the quantifications for those elements. So it's best to make sure we go through each. I can then click Save, and then pick an area to save that calibration file. And that will create a calibration file that is gl1.cfz. So that is the case with my vacuum data. Now this is taken under vacuum conditions, which means I've got my sample sitting on my tracer and I've got a vacuum within the nose of the tracer. To get a sense for how that works, let's look at sample BL122 here in red. Here, we're going to once again bring up each element in the sequence. Silicon, phosphorus, sulfur, potassium, calcium, titanium, iron. So here we see each element taken under vacuum conditions. What happens when I take with helium? Now, this is an important note because lots of folks want to be able to quantify using helium. In this case, I'm going to select the same reference standard, collected under helium conditions. That spectrum is now in green. This spectrum was taken for about the same time as our reference spectrum in red, which is vacuum conditions. Now, in this case, the helium is removing the window of the instrument, which is about 4 microns thick of proline, which helps reduce the attenuation for light elements, but most importantly, helium is saturating all of the air between my sample. So here in green, you can see I'm getting a much higher record of silicon than I was before. This is increased even higher for aluminum. The real big difference you see comes with magnesium. Before it was barely visible, now I have a better defined magnesium peak. I can even start to see sodium right there compared to the non-existent sodium in my vacuum spectrum. So in this case, magnesium, I'm getting a much better definition of the peak. One would expect that my calibration for magnesium would be much better with the helium data set than the vacuum data set, since we are much more sensitive to light elements. But let's take a look at that assumption. So if I come over here to S1CalProcess, create chem file, I'm going to select here. You can see I have my helium spectrum here. There's my normalization for helium, and my helium reference is going to be GL3. Now, just for a reference, if I click OK for GL1, this is the vacuum spectrum. For magnesium, my average error was 0.35. So the error for little peaks like this was 1/3 of a weight percent. How much better will it get when I'm using helium? Well, let's find out. I come over here to S1CalProcess, create chem file, and we're going to do GL3, same normalization. I click OK. And for magnesium, I have higher error using the same corrections. Now, part of this is because I'm much more sensitive to aluminum, as you can see right here. And aluminum creates a matrix effect for magnesium. You can see that magnesium is now on the slope of magnesium, whereas before they were much more discrete. So I can add in aluminum as a correction factor, but that only does so much. In fact, my average error for magnesium for helium is the same as it was with vacuum conditions. 0.34 weight percent earlier, now it's 0.32. But I can see here my magnesium signal is much bigger. Why would I have similar error if I'm getting a better signal in the spectrum? The culprit is over here, rhodium. Our quantification, just to review, our quantification, create chem file, is 0.28 to 0.31 for both vacuum and helium. If I come over here and add in my vacuum reference spectrum, I can see here rhodium is relatively consistent. Normalizing to rhodium is not that big of a deal for these elements. Let's now look at what happens when I use the helium data set. So here's the helium data coming in. Look at how much more variation I have in the rhodium. It's not nice and neat like it was before. This is a consequence of the fact that we've removed that proline window. And thus, instead of rhodium L lines scattering around 4 microns of plastic, they're scattering across the surface mineralogy of the mud rock reference standards. This adds a tremendous amount of variation. You can see here my magnesium is just fine before normalization. But when I normalize, like I was earlier, I mess it up. Look at all this variation now in the magnesium. The baseline is completely off. My rhodium is just too variable, and there's nothing I can do about that. In fact, normalizing to different parts of rhodium are going to create even more severe problems. So what do? The answer is I choose a different normalization. It's very messy normalizing to rhodium right now for magnesium. But if I normalize out here in this region, I get much better peaks for magnesium right there. So in this case, I want to change my normalization to something below 1 keV. So for GL3, we're going to normalize to 0.9 to 0.7 to 0.9 and avoid that rhodium peak entirely. I click OK. Now my magnesium error before was 0.3 weight percent. Now for magnesium, it's 0.1 weight percent. This is an example where Compton normalization is critical. The only way to find out the right normalization is to look at your spectrum first and look for a place that's varying with no clear elemental overlaps. This requires a little bit of time, but trust me, it is worth it. So that emphasizes why normalization is important. Let's now go through an experiment, and we're going to do our quantification, but this time we're going to make 2 changes. We're going to add an element, we're going to add a chemistry file first. So in this case, I created for GL3, I want to add a new reference spectrum. To do that, I come over here to PDZ files, I come over to S1CalProcess, and I select Insert PDZ. Here, I created a spectrum under helium conditions. We're going to call it Test Edition. I click OK, and I look. It's measured using all the same parameters. So now I come over to GeoChem, S1CalProcess, Add Remove Chemistry Files. And now if I look, I have a new file, Test Edition, at the very bottom. For GL3, my helium cal, I'm going to add in Test Edition. So that inserts a new reference standard. If I look down here, for GL3, I have that value right here. It's going to just copy the photon counts from above, but once we go through the calibration, it'll correct itself. If I come over here to my known values, though, Test Edition is empty. Why is that? Well, it's a test. This isn't actually a reference standard. So in this case, but if it was, I would have to add in known values. These known values are typically taken from neutron activation analysis or ICP-MS. Here, we're going to make it deliberately wrong. We're going to make it 5 weight percent across the bat for every element. This is just to show you how much variation a single bad reference standard can create in your sample. But be aware, when you're actually adding in a real reference standard, you want to put in the exact quantities. Now I come over to S1CalProcess, create chem file. We're going to do it for GL3. We will keep using our normalization that we know works. Click OK. And now we review. So here, my quantification for magnesium has increased slightly, 0.37. If I look here, look at my givens, I see that, by and large, I have pretty good. In fact, I look at the difference. There's a difference of 0.25 weight percent, 0.14. This is all reasonable. But going down the list, bingo. This sample, test edition, has a variance of 4 weight percent. That's quite a lot of error. So in this case, what I want to do is correct it. And I want to remove this particular reference spectrum that adds a lot of variation. I do so, and my variation drops down to 0.1 like it was before. So with test edition, I have a lot of variance. Without it, I start getting a much higher accuracy. I come down to aluminum. Lo and behold, I have the same problem. Test edition is adding lots of variation. Not a lot, but a fair bit. I can remove test edition, and I get a more reasonable number. Silicon. My average difference is 2.5 weight percent. I come over here, and I can see my differences, and I see my big difference is test edition. My quote known unquote is 5 weight percent. Remember, I made this value up. The calculated indicates it should be 26 weight percent. So I say this is not valid for there, and I remove, and voila, my error goes from 2.5 to 0.8 weight percent. So you can see here that adding and removing reference standards is quite important for this case. But nonetheless, I can continue to create a quantification using this and create that quantification model. In any case, I can come out here. I decide I don't want this. By the way, if you look over here, you see that it's now properly updated the photon counts. If I want to get rid of that, I add remove chemistry files, select GL3, test edition, remove, and now it's gone. So I can go back and improve my calibration. I can also add a new element to a calibration. In this case, I come over to add remove elements, and I'm going to add, let's say, for these light elements, I'm going to add the M line of lead. So if I come over here to my knowns, I can see now that I need to add a new concentrations for lead in these samples, which can easily be done. But nonetheless, this gives me an idea of how I go about adding and removing new elements to calibrations. Now, one of the last things to discuss is what is the most appropriate reference standard and range of variation. Well, that depends on the different elements you're looking at. So for example, if I come over here, maybe this magnesium is too high. This is about 7 weight percent. So if I want to, I can come in here, S1CalProcess, create chem file, select GL3, (0.7 to 0.9), and I can begin the correction process. So there you see your error back to 0.1 that you saw. But if I look over here, I see I've got one value that is 10 weight percent, RTCW 260. Maybe that's too high of a magnesium number, and I don't want to create any kind of variation in my statistics. So in that case, I can come over here and narrow the range of variation to something a little more reasonable. If that's reasonable, it depends entirely on your sample. So in this case, I can start to tailor the calibration to the expected results that I have. The easiest way to get to those expected results is to use RTEX and overlay your spectrum so that you can start to see which values are correct or not correct. A quick example of that is right here. So in this case, I've got my mud rock set, and each of these represents a different line and a different peak height for the calibration, just like over here. Except in this case, they're all colored the same. This is also for the mud rock cal. Here, we were looking at which is going to provide the best quantification. We wanted to see if mud rock was appropriate. So we came down here, and we looked at manganese. This is the variation in the manganese calibration. We can see here it's relatively modest. We add in our standards, or our samples, And we see that they have higher manganese than our spectrum allows. Here's the limit of quantification based on the spectrum, and there's my high for manganese. In this case, this wouldn't be an appropriate calibration to use. So you can use simple peak overlaps, and that's to see if a calibration is appropriate. And that is really the best way to find out if a calibration is appropriate. The other thing you can do is rely on the literature provided by the factory who's created your calibrations. In this case, you can see my quantification limits between 1 part per million and 3 weight percent for silver and copper, for example. These can be reliable as well, but they will never be as good as directly relying on the spectrum. I hope this answers your questions about quantification using S1CalProcess. It's a powerful tool, and you can incorporate physical parameters here to assist with your quantification. But it's important to remember, always pay close attention to your spectrum and go from spectrum to the quantification. As we like to say in archaeology, it's best to work from known to unknown. Thank you, and if you have any questions, please don't hesitate to contact us.